first and foremost, thank you very much for joining the call today. Myself and Beatrice will be walking you through our presentation that is called Addressing a 3 Terawatt-hour Cell Deficit by 2040, and we'll be examining the role that battery recycling and emerging technologies might play in bridging that gap. So as Michael introduced me earlier on, I work as our Product Director of New Technology at Benchmark. Really, that division covers everything from battery recycling through to next generation battery technologies like solid state batteries, lithium metal batteries, silicon anodes, and sodium ion. But the company itself covers much more than this. I'm joined today by Beatrice Browning, a senior analyst in our battery recycling team. And before we kick off the presentation, I'll just tell everyone on the call a little bit about Benchmark, in case you don't know who we are. So Benchmark itself was founded back in 2014. It was initially founded to just track pricing for lithium and graphite. And as many of you will know, lithium graphite back in 2014 weren't really significant demand drivers. The battery industry, lithium and graphite, were small fries. As that industry has grown really quite significantly over the last 10 years, Benchmark's grown with it. As a result of that, the company now publish more than 100 price assessments and market data reports across the lithium-ion battery supply chain, all the way from upstream minerals such as lithium, cobalt, graphite, nickel, all the way through anode and cathode to battery cell. And we've recently acquired a company called Romotion that track the downstream really quite closely, looking at electric vehicle sales, looking at plug-in hybrid sales, looking at ESS rollout, portable electronics. The company now track everything from mine all the way to market. The company also has a forecasting division. Myself and Beatrice are parts of this, forecasting these markets all the way out to 2040, where the presentation is going to be focused today. A consultancy division that offers bespoke projects from pre-feasibility and due diligence, all the way through financing and scoping market opportunity, and a benchmark source platform, which is kind of your one-stop shop for understanding daily market news across the battery supply chain and the broader energy transition. So without further ado, I'll kick off the presentation, start with that marketing, pass over to Beatrice to run away.
Great, thank you so much, Rory. So yeah, if we start by setting the scene on the lithium-ion battery market, lithium-ion battery supply chain, we can think about lithium-ion batteries going from their beginning all the way through to scale up. And at the moment, we sort of claim that we're entering the 4th chapter of the lithium-ion battery story. So when we think about the previous chapters, chapter 1 involves the invention of the lithium-ion battery and lab scale development, so many years ago now. Chapter 2 will have been the early commercialization in portables and optimization of that chemistry. So what we think about there is the commercialization of the lithium-ion battery by Sony in the early 90s. Then moving into chapter 3, which is where
anyone.
Hello? Okay, I'll carry on there. Then we're moving into chapter 3, which is the chapter that we're currently in and coming towards the end of, which is that industry scale overhaul. So thinking about the gigafactory scale of lithium-ion battery manufacture, optimization. Oh, you can't hear me. Can anyone else?
We can hear you.
We can hear you.
You can hear me, okay. There might be a sound issue. I had some bandwidth issues earlier, so I appreciate that, you know, it can be a bit of an issue.
There are some people that are not muted. Maybe the moderator can mute the other people.
I think the problem got solved.
Solved? Okay, great. I'll carry on then. And yeah, going to chapter 3, we have the industry scale overhaul. So that's, you know, gigafactory generation of lithium-ion batteries, you know, orders of magnitude greater than ever seen before in the portables industry as we move into EV and ESS industries. And then finally, as mentioned at the start, we're moving into that 4th chapter of the lithium-ion battery story, which is growing the lithium-ion battery supply chain, developing it, scaling it, considering new emerging technologies as well, and specifically recycling. So as lithium-ion batteries went from startup to scale up, the cost has been driven down. This is a natural economy of scale. You know, what we saw in 2015 is costs were as high as between $200 and $250 per kilowatt hour. And as cell production has increased, as optimization and mass production has developed, what we're seeing is that cost is being driven down. This is a natural progression. In 2024, we saw that the cost of development for a lithium-ion battery was between $65 and $80 per kilowatt hour. What is worth also mentioning is that emerging technologies as well, they're high cost at the moment, but with optimizations we're seeing within the lithium-ion battery industry, we're going to see the costs being driven down as we go through in upcoming years. In 2024, we saw a year of uncertainty, particularly within North America and Europe, when considering battery electric vehicles and plug-in hybrid electric vehicles monthly sales. So at the start of the year, we saw a general uptick in the US sales, beginning to slowly then increase as the year sort of went throughout, and towards the end of the year, we saw a slight uptick again. Within Europe, we can also see fluctuations throughout the year, but a general decrease in overall. What's key to point out here is this is just a fluctuating sales trend throughout the year. There's been a sort of negative narrative towards the EV downturn, but actually if we look at the bigger picture, we can actually see that the battery electric vehicle and plug-in hybrid electric vehicle penetration rate is just a very small bump in the road in 2024. So the narrative is not forecast to remain sort of negatively as you look out to the long term. We can see that penetration rate is set to almost triple all the way out to 2034. Then considering unit sales and the global distribution of these sales, we can see that there's a current dominance in China, as expected due to that industry dominance that has always been the case as we've been developing the industry. But we can see that there's a more even global distribution of sales across the globe forecast out in upcoming years, with Europe and North America establishing those lithium-ion battery supply chains, encouraging those sales within those regions in upcoming years. Now considering regional trends from a demand perspective, again, we can see that Chinese lithium-ion battery demand will dominate due to large EV and ESS sector growth. So we can see that 46% of the market in 2024 came from China. Market demand came from China. And looking out for 2040, we'll see this decrease down to around 42%. And again, this is through other regions that are starting to influence the market. So within North America and Europe, we'll see battery demand increase. And we'll see a compound annual growth rate of around 21% between now and 2030. And it's clear that the requirement for lithium-ion battery supply across the world is going to be of paramount importance. So looking even further out to 2040 and considering the supply versus demand scenario, we see that cell demand in the base case scenario is forecast at around 8 terawatt hours. But based on the current supply pipeline, there's going to be a 3 terawatt hour deficit in supply, hence our title of this presentation. So with this deficit comes an opportunity for markets to really develop, specifically the recycling and emerging technology markets that can help to plug this gap. And that's what we're going to explore during the course of this presentation. So when considering cell demand, it's also key to consider cell manufacturing capabilities, which are in turn determined based on critical mineral supply. The supply of battery raw materials are fundamental to this supply chain. So looking at lithium, nickel and cobalt, we can see that there are actually forecasted supply deficits coming. For lithium and cobalt in the base case and for nickel in the high case, this will arise before the turn of the decade. Looking into the base case across all markets, you can see that mining is going to be critical, will be a critical bottleneck in supply. And one way in which this gap can be plugged is through recycling, which I'm going to explore in a few slides' time. So considering volume of material, we can see that there's a significant demand for each raw material market between 2024 versus 2030. And in order to reach the forecasted demand, we need to consider nickel, lithium, cobalt from the cathode perspective, and graphite and copper from the anode perspective, all of which are really important materials to take into consideration. Translating this into the number of mines, we can see just how much mining capacity is actually required. Mines take quite a long time to come online, anywhere between 5 and 25 years. So that's something we have to take into consideration here. This is much longer generally than building a recycling facility, which is also something to take into consideration, as well as energy intensive and ESG concerns that are surrounding building and mining practices as well. So yeah, overall, it's key to outline that unlocking investment holds the key to meeting market ambitions, and $571 billion worth of investment is required to meet 2030 demand. Looking out to 2040, this required investment is set to triple, so around $1.6 trillion of investment is needed in the battery industry by 2040. It's key to highlight that the largest capex growth to bridge the gap will be for recycling, so we'll need $157 billion in global investment in order to localize secondary supply of critical battery materials. Additionally, emerging technologies can offer an avenue for raw material diversification and the options for tailor-made manufacturing of batteries, so thinking about bigger, faster, further versus more efficient batteries and fit for purpose. And Rory will outline the emerging technology side of this later on in this presentation. But for now, to speak on the recycling side of things, we can consider two overarching themes that underline why we need to recycle batteries. So firstly, from a supply chain perspective, we can think about supply constraint mitigation. That's considering those deficits that I mentioned for critical mineral markets that are going to be needed to be plugged. And process and end-of-life scrap recycling will enable secondary supply to close that gap. We can also think of ESG risk mitigation for lithium-ion batteries. So that's environmental, social, and governance concerns. So thinking about environmental impact of traditional mining, social and governance concerns for mineral-rich regions, and geopolitics that might affect accessibility of raw materials. Finally, we have supply stream localization on this side of the coin, which thinks about domestication of recycling to ensure you have a localized supply of critical minerals. And increasing recycling capacity and scrap availability means that we can have that localization. And then on the other side, we can think of incentives for closing the loop. So firstly, having a robust recycling market and infrastructure will be essential for the circularity perspective of things. The cost benefit, extracting value from waste produced during cell manufacturing, otherwise known as process scrap, will be key. And also recycling provides revenue. These materials are going to be in high demand, and so with high demand comes a cost benefit as well. And finally, policy momentum, so increasing regulation for collection, reuse and recycling of batteries alongside recycled content targets within new batteries has really sparked that interest for the recycling market. And it's just key to mention as well that all the data displayed in the next slide is going to come from Benchmark's recycling forecast analysis of the recycling market and expected scrap pools from process and end-of-life based material. So looking at this analysis, what we can see between 2024, 2033 and 2040 is the changing market distribution of process and end-of-life scraps. So just to reiterate, production scrap or process scrap is scrap that comes off the production line during cell manufacture. End-of-life scrap is scrap that comes from end-of-life lithium-ion batteries. And so in the short term, in 2024, we saw that the vast majority of scrap available in the market currently comes from process scrap. This is because, there's a low volume of batteries that have actually reached end of life. There's an expansion into the EV and ESS markets, but they're only just being put into operation. As we look out into the medium term, we see an inflection point by 2033, where gigafactory capacities come online, there's production scrap being generated, but there's also end-of-life batteries that are reaching the scrap pool and beginning to reach end of life. Looking out to 2040 in the long term, we obviously gigafactories will have been online for a while, production losses will be streamlined, and many more batteries are going to reach the end-of-life scrap pool. So what we can see is there's going to be a really key involvement scrap within the recycling market. And what is key to highlight here is the combined scrap pool is forecast to grow by more than 20 times between now and 2040. Now thinking about approach to recycling, many companies adopt different approaches to recycling. Some take batteries through to intermediates in the pre-treatment stage. This can be through mechanical or pyrometallurgical treatment of batteries, mechanical being shredding batteries and separating out critical components, pyrometallurgical being burning batteries and generating alloys that are composed of nickel and cobalt rich material, for example. And then there's also facilities that take intermediates that are generated from the The dominant process we see in the market for this is hydrometallurgy, and battery-related chemicals includes battery-grade precursors, technical-grade precursors such as lithium carbonate, nickel, cobalt, and manganese sulfate, for example. Also mixed hydroxide precipitates, hydroxymetal concentrates, PCAM, which is precursor cathode active material, and CAM, which is cathode active material. And again, other approaches can include integrated capacity, which would mean taking battery inputs and going all the way through to those battery-related chemicals. So there basically are an array of approaches here that you can generate them. Generally, we see pre-treatment facilities and recovery facilities using mechanical and hydrometallurgical processes, although it's key to point out that there are other processes that are being used. And then focusing in on black mass. What we see is battery black mass is a key material that's generated within the recycling market, and it's a tradable commodity, so much so that Benchmark has a black mass pricing team that tracks the trade of this material between stakeholders across the globe. Black mass is a variable commodity, and it's a processing intermediate that comes from pre-treatment and separation out of cathode and anode active powder from other cell components. This powder, known as black mass, contains the valuable lithium, nickel, cobalt, which leads to price black mass, and it's sought after across the market. So considering the movement of black mass, so the majority of recycling capacity currently in the West right now is for that pre-treatment stage to generate black mass. And there's quite a fair lack of refining capacity in the West. That being said, there are refining operations coming online and a lot of investment is being made in order to localize this refinement. And in the East, there's an abundance of refining capacity and a need for feedstock. So bidders are often willing to purchase this Western black mass, hence we see this flow. There's higher purchasing power within China and rest of Asia at the moment, just because there's a high amount of refining capacity. There's the overheads that are involved, and so there's quite a valuable business opportunity for them to purchase this black mass, particularly when there's a low availability of feedstock. Then considering the flow of black mass from Asia into China. So in the past, there's actually been an import restriction of black mass into China due to it being classified as a hazardous material, meaning black mass has been processed and is normally black mass is normally sent from the West into Asia, outside of China, where it's processed into a mixed metal product, such as metal hydroxide that I mentioned, which can then be processed by the battery chemicals into China because it's no longer coming as black mass. What's key to point out, though, is the Chinese import ban on black mass is set to be relaxed in upcoming months. There's been many rumours of when this will actually be, anywhere between 6 to 12 months. So again, though there's refinement capacity that is being localised within the West, there's other restrictions that are being lifted within China that may actually still encourage that leakage. So for countries where leakage is happening, this is really an issue. And to localise raw material supply and reduce reliance on imports, keeping black mass contained is really important. So one way to do this is through classification of black mass to harmonise its movement within a given region. So spotlighting the US, the European Union and China. So in the US in May 2023, the US Environmental Protection Agency issued a memorandum which stated that black mass is not a universal weight and is no longer a battery. But until the recycling process is complete, it would remain a solid waste, which means that although there's no federal regulation, it would fall under state and local solid waste regulations. So it sort of highlights that black mass has been acknowledged, but it doesn't actually highlight just exactly how it should be defined across the bloc. Within Europe, towards the end of last year, the European Commission unveiled post-agency Europe feedback, in which it was outlined that intermediates of the battery recycling process should be classified as waste. This proposal did not, however, mention the term black mass at any point. The feedback that came back outlined a number of questions surrounding black mass definition and black mass classification in order to harmonise movement of this material across the region. But what was outlined is that generally black mass was going to be thought of as a waste material. And then in China, as stated, the hazardous waste classification of black mass is set to be relaxed in order to encourage material to move within the region. All of this legislative effort basically highlights the requirement for regional retention of black mass in order to ensure there's localised raw material extraction. Then considering extraction of battery materials from black mass, this slide basically illustrates how lithium contained within the lithium-ion battery scrap pool presents a valuable opportunity for the secondary supply to plug the demand gap in the lithium market, just as an example. So lithium from secondary supply has the potential to meet around 5% of demand in 2024, which could actually grow to 27% by 2040. With advancement of lithium refining technology and increased recycling capabilities worldwide, this highlights the true value of the recycling market in bridging the forecasted raw material market deficits. And then finally, considering lithium contained within the scrap pool and how this lithium could be translated into battery cell gigawatt-hour volumes, it's clear that lithium from recycled sources could be utilised in cell manufacturing to produce around 2 terawatt-hours of battery cells by 2040. In order for each region to make the most of the lithium contained within this localised scrap, controlling material flow is essential. So with black mass generation being a key part of the supply chain, controlling black mass flow is going to be critical in securing regional supply. So now that I've highlighted the requirement for recycling bridging the gap, and I hope I've convinced some of you here, I'm going to hand on to Rory to define the role that other emerging technologies can play.
Perfect. Thank you very much, Beatrice. So yeah, I think Beatrice really did a fantastic job there of summarising the role of recycling in the battery industry out to 2040. Really, it kind of pitches a world where, although the rest of the world is largely catching up on that raw material and midstream supply to meet that downstream demand, there's two kind of caveats or levers in play there. You have raw material mining and refining to deliver that fresh virgin material. And then you have any electric vehicles, any ESS units, any portables which are within a region, potentially leaking into other markets. And rather than allowing that capacity to leak by regionalising, maintaining and reprocessing that supply, as Beatrice showed, up to 27% of the global demand could be plugged by the emergence and innovation in recycling technology. Now, Beatrice has done a fantastic job there. It's my job to walk you through a few different battery technologies which are emerging over the coming years, the coming decade out to 2040, which Benchmark follow closely and believe could also play a role in plugging that 3 terawatt-hour supply demand gap. So the first strategy we're going to look at today is diversification of materials. If we look at traditional lithium-ion batteries, what we see is that lithium, nickel and cobalt, as shown by Beatrice earlier on, are all forecast to enter a market deficit before the turn of the decade. The graphite itself on the anode market, although it has a more balanced supply demand beyond 2030, we see other geopolitical risks, with China currently dominating more than 95% of that midstream graphite anode market. Diversification here will be needed on globalization in order to alleviate some of those geopolitical constraints. And then you have other materials like manganese and iron, which are used in cathode chemistries for lithium-ion batteries, with highly established industrial use cases where refining could be a bottleneck, getting the purity required to produce those materials, but much more abundant and much more sustainably sourced. As we look to alternatives for lithium, sodium is the one that's often brought into the conversation. Now, sodium-ion batteries have been developed for about as long as lithium-ion batteries. However, it's taken them a bit longer to find their commercial footing. We've seen really quite significant progress in China over the last few years. We've seen rollout of early sodium-ion batteries, but really they're still finding that commercial drive and commercial push, especially in the new price environment of lithium-ion batteries. But the dawn of sodium-ion batteries could alleviate some of that stress on lithium-ion supply, and we'll explore that a little bit later on. When we look at the anode side, one of the key technologies looking to revolutionize and diversify anode technologies is silicon anodes, where the traditional market is currently dominated by China. Silicon anodes are spread across the globe. We're seeing innovation in North America, Europe, rest of Asia, China, in the development and rollout of traditional low weight percentage silicon anodes, but also in innovation and development of silicon anodes that can push that loading up really significantly. Within that box, we have a whole load of emerging technologies, redox flow, iron air, multivalence batteries, many more. The list could really go on quite significantly. The other theme we're going to follow today is looking at improving material intensity, making the same amount of tons of material go further. And where the industry is really pushing at the moment is anode innovation as the kind of next frontier or next step increase in battery cell capacity. Looking at it from a graphite perspective, we can see that graphite has a specific capacity of around 372 milliamp hours per gram. That's theoretical, and in the same vein, when you look at silicon and lithium metal, the theoretical capacity is about 10 times higher. Now, in a practical setting, it's more like sort of 2 to 3 times that it's likely to be achieved in the near to midterm, but still some really quite significant improvements over those traditional graphite technologies. That brings us back to what Beatrice said earlier on. We've got this kind of divide at the moment where some are pushing towards next-gen technologies, really driving the performance of battery cells and battery packs. We're talking 1,000-kilometer vehicles, we're talking less than 15-minute charge times, but there's an alternative route where by improving the technologies, by improving that energy density, we could have the same size packs or reduced size packs that go farther, take less raw materials, and give the same performance that we have today. So breaking those into sections, what role do emerging technologies play? Firstly, we're going to focus on the sodium-ion battery, where it might play a role, what that commercial landscape looks like today, and what it looks like in the future. We're going to look at silicon anodes, which sit somewhere between the two. They sit in that diversification landscape, being developed globally, enabling a move away from full usage of graphite materials to silicon graphite blends, or in some cases, silicon dominant anodes. That increased energy density can improve that material intensity and performance of cells. Another technology of note is solid state technologies and lithium metal anodes. Within today's presentation, we won't touch on these, but it's worth noting that Benchmark's new technology division covers all of these industries, forecasting supply, demand, and market dynamics out to 2040. So quickly focusing in on the sodium-ion battery first, the ability to kind of alleviate some of that supply stress on the lithium-ion battery. Sodium-ion batteries and lithium-ion batteries are very similar in the way that they operate. They both operate by this rocking chair mechanism. What happens is that the alkali metal ions, be it sodium or be it lithium, are stored within a metal-based cathode. Upon the charge cycle, those ions are physically removed from that cathode structure. They migrate through the electrolyte and they're inserted or intercalated into a carbonaceous anode. The only difference really between the lithium-ion battery and the sodium-ion battery is the ion that's used to carry that charge. Energy is then passed around your system, given the potential difference between your cathode and your anode material. Some key differences between lithium and sodium are that the sodium ion is significantly heavier and larger than the lithium ion. And at the anode side, sodium-ion batteries tend to use a hard carbon or a soft carbon amorphous structure, whereas lithium-ion batteries use very well-ordered graphite. This hard carbon is much less dense than graphite is, and the result of this is that sodium-ion batteries, generally speaking, have a lower energy density than lithium-ion batteries. Now, the comparison I've put on the screen here is a little bit unfair. I've compared sodium-ion batteries to kind of state-of-the-art NMC 811 plus cells. A fairer comparison would be to compare them to LFP-based cells. Here, what we see really is that sodium-ion batteries that are being developed today kind of match or meet that low to mid performance that you see for LFP technologies. And the hope is that the technologies which are currently being developed for commercialization may be able to stretch to meet roughly parity of LFP cell performance going forward. Now, some benefits of sodium-ion batteries. I discussed the use of kind of abundant raw materials there. If we look at the upper continental crust concentration of lithium compared to sodium, it's clear that sodium itself is very abundant. Now, that's a relatively simple comparison. Getting sodium that's battery ready is significantly harder than simply scraping it up from the Earth's crust. However, that availability is really quite large. When we look at the raw materials used for other parts of the cell, for traditional lithium-ion batteries, we have that lithium, nickel, and cobalt, which, as Beatrice showed, are all set to enter market deficits by 2030. And when you look to the sodium-ion battery cathode chemistries, they tend to use materials like manganese and iron, and also in many cases, vanadium. Each of these three materials, manganese, iron, and vanadium, as their markets are largely driven by consumption in the steel industry. More than 90% of demand for those markets comes from there. And so instead of the issue for these supply chains to scale being mining, which can take anywhere between 5 and 25 years, depending on the maturity of the site, the location, and the difficulty extracting the resources, each of these materials, the bottleneck really is that refining capacity, which can come on a lot faster, taking those raw materials that we have and upgrading them to the battery-ready precursors to be fed into the sodium-ion battery supply chain. Another few potential benefits of the sodium-ion battery are potentially lower cost. These abundant, sustainable, easy to source materials should be lower cost. However, as Beatrice mentioned right at the start, having a technology and an industry that's really at the start of that ramp up and scale up phase means that technologies today likely won't be cost competitive. They have a wide range of operating temperatures, high performance high performance in high temperature and low temperature environments, and potential to improve safety. It's something that's often stated around sodium-ion batteries. They're much safer than lithium-ion batteries. One of the key caveats to this is that you need to replace that copper current collector at the anode with an aluminium version. We're seeing some cells come out with dual aluminium current collectors, but some of the cells that are being produced today still do contain those copper foils. Looking into the sodium-ion market sentiment and where it might be going, if we flash back a little bit to 2021, when lithium prices were at their peak, they peaked in December 2021, January 2022 at around $80 per kilo. At that time, we saw a huge upswing in sentiment in the industry. We saw massive capacity announcements across the world, and it was really put forward that sodium-ion was a cheap solution in order to alleviate some of this supply pressure on the lithium-ion market. Fast forward to today, and what we've seen is the lithium prices have fallen really quite significantly alongside all battery raw material prices, as low as $10 per kilo at their lowest point. This has really led to kind of a dampened sentiment in the sodium-ion battery market. We've seen a lot of players begin to pull back on their manufacturing commercialization timelines, but it's really key to stress here that those with significant progress towards delivery of a sodium-ion battery haven't stopped their research and development, haven't stopped their pilot scale manufacturing, and more than ever, we're seeing sodium-ion ESS units especially enter the Chinese market, going through their demonstration and qualification procedures. So as we look towards that midterm forecast, what we've seen is that as lithium prices have fallen, sodium-ion batteries have gone into a consolidation and demonstration phase. If we look at Benchmark's long-term lithium incentive price, in order to ensure that that forecast supply deficit in lithium is met, that incentive price must increase to bring those miners at the higher end of the cost curve into profitability. As a result of this, we expect lithium prices and broader raw material prices to increase and bring sodium-ion batteries into the situation where that research and development and consolidation, which has gone on over the past few years, enables them to make that commercial market entrance. So if we start looking at a sort of demand forecast for the sodium-ion battery, what we see is that the market's largely driven by the ESS sector today, where the sodium-ion batteries fit is in that low temperature, high temperature performance segment, reasonable cycle life, reasonable cost. Beyond this point and beyond 2030, we see the EV demand being the key market driver for sodium-ion batteries. When people hear EV for sodium-ion batteries, there's often a visible cringe. Sodium-ion batteries will never compete with NCM 811 technologies in your high-performance, long-range electric vehicles, but they do have a very serious home in 2- and 3-wheeler applications and short-range EVs. In total, at the moment, Benchmark forecast 425 gigawatt hours of sodium-ion battery demand by 2040, with the largest demand driver being that EV segment. The idea here is that 425 gigawatt hours of sodium-ion battery capacity can fill that gap at the low and mid-performance side of the demand curve, enabling lithium, where it's energy dense, where it's high performance as part of nature, to alleviate that higher performance segment of the market. So that's the real message here on sodium-ion batteries. The job of sodium-ion batteries when commercialized is to alleviate that supply pressure on the lithium-ion batteries, freeing up that critical lithium for those mid to high performance specifications. So where those sodium-ion batteries rely on the abundance of materials, the sustainability of feedstocks, and potential cost for achieving their commercial targets, we have materials like silicon and lithium metal, which is aiming on driving performance in order to push that commercialization. So these technologies really push the boundaries of what we know lithium-ion batteries can do today. We're seeing a lot of early market movement in the likes of military applications, in the likes of eVTOL, sort of minor aviation applications, But the hope is that if these materials want to go mainstream, you have to reach a cost perspective. You have to be able to reach $1 per kilowatt hour level that is comfortable for the consumer to take on board. Today, we're going to look at silicon anodes specifically, although I'm more than happy to answer any questions afterwards about the solid state and lithium metal battery segment. It's an area that Benchmark have been covering for just over 3.5 years, but today we'll be focusing on the silicon anode. So to understand the silicon anode and the material it's looking to complement, we need to understand a graphite anode first. Graphite operates by lithium intercalation. Lithium ions move through the liquid electrolyte. They're inserted between graphene sheets, and 1 lithium ion is stored per 6 carbon atoms in this framework. If we look at a silicon, how silicon intercalates or interacts with lithium, it's through an alloying mechanism. So lithium here doesn't intercalate into the silicon structure. Instead, it physically interacts with the silicon, and each silicon atom can store almost 4 lithium ions reversibly. It's around 3.75. This increase in lithium storage enables silicon to have a much higher capacity than its graphite alternative. And if we look at the positive aspects, what we see is that there's a 10 times theoretical capacity increase going from graphite to silicon. As I said earlier on, in a practical setting, it's closer to 2 to 3 times that we're likely to see. And silicon can also enable fast charging. It's expected that a reasonable target for fast charging of these anodes would be below 15 minutes, with some in the market claiming charge times as fast as 3 to 5 minutes. However, when we look at the downsides of silicon, it's not all rosy. Silicon itself, this new mechanism where it takes on up to 4 silicons, we see 300% swelling of the material. That causes quite significant mechanical degradation. The solid electrolyte interface, which is formed as a protective layer on the silicon surface, can degrade, reform, degrade, resulting in constant electrolyte degradation. That high surface reactivity both reduces the cycle life or operation lifetime of your silicon anodes, and also the calendar life during storage, reactivity with either air or surrounding components, liquid electrolyte, etc. When we look at the silicon market, silicon anodes aren't new. They've been around for a while now, well over 10 years in some battery cells. But the key reason that Benchmark started tracking this market, and the key reason we believe the next few years are really critical in its commercial pathway, is that we've seen this huge increase in pipeline capacity. Beyond 2018, that market share gets even smaller. But as we've seen from 2023 to 2024, the capacity of silicon anode manufacturing increased by 236%. And between this last year and this year, we expect that capacity to increase a further 139%. So this commitment of capital, this investment in the industry and this construction of facilities specifically for the production of silicon anodes is a huge bull flag for the industry, and something I think worth paying attention to if you're thinking about how we might diversify and improve battery technologies today. A bit of context here, the yellow bar is traditional silicon anodes. Broadly speaking, they're limited by that volume expansion to below 10 weight%. What we're seeing in the market is most of those materials are loaded at about 3 to 5 weight%, and the highest I've seen is around 8 weight% today. These have led development. Technology never stops, and China seems to be highly committed to getting that weight% loading up to around 10%, and is where a lot of the pipeline capacity we've seen out to 2030 comes from. However, we've also got these engineered silicon anode active materials, which are using novel nanostructures and techniques in order to contain and utilize that swelling, pushing silicon loading anywhere from 10 weight% all the way up to silicon dominant anodes that can use sort of 80 to 100 weight% silicon. Key thing to note on this slide before I move on is this shows pipeline capacity. This is built facilities by the end of a year. In order to understand true commercialization and how market rollout's going, you need to forecast production, which is a measure of supply, understanding ramp-up rates, understanding utilization, and understanding that qualification process. So now on to the title of the presentation, a 3 terawatt-hour supply deficit. So if we look at the anode market in 2040, taking into consideration graphite, engineered silicon, and traditional silicon anodes, which are 3 of the key supply drivers, we still forecast this 3 terawatt-hour supply deficit by 2040. If we look at graphite alone to bridge that gap, we need more than 2,000 kilotons of additional supply in order to account for that deficit. If we look at some relatively ambitious scenarios for silicon adoption, we can see that raw material requirement in tons to bridge that gap can reduce quite significantly. So with just 30 weight% silicon, we can reduce that by more than half. Now, really the key point to make here is that today we're seeing relatively low weight percentages of silicon materials. That 30 weight% scenario will require a huge amount of technical progress, a huge amount of commercial adoption, and widespread silicon adoption across the globe. However, what we see is that as these new technologies begin to enter production, that material requirement for energy, that tons per kilowatt hour or tons per gigawatt hour, can reduce quite significantly, and silicon can play a role in both alleviating that supply pressure and improving the performance of battery cells. So this takes us back to those two scenarios I discussed a bit earlier on. The one that's most commonly put forward for next-gen high-performance applications is maximizing performance output. It's cramming as much energy density as possible inside the same pack size. This is where we talk about silicon, we talk about solid state and lithium metal, we talk about 1,000-kilometer drive range. So the question I pose is that what we're looking for with these next technologies is we demand both an 1,000-kilometer drive range and a 15-minute charge time. But is that really what new technology is for? Is there not a world where if you have an 1,000-kilometer drive range, in order to exceed this, you would need to drive for 8 to 12 hours at a point where you would want to stop off and brake, or a 15-minute charge time? If you could drive for 6 hours, park up, get a coffee and charge your car, would that not be sufficient in order for that technology to serve its purpose? So the two scenarios we're left with are bigger, faster, further, pushing technologies as far as they can go to give us the best possible outcome for our battery packs, or making technologies highly efficient and better fit for purpose. Understanding that every new technology, every battery chemistry has its own strengths, its own weaknesses. By understanding the use case and the specifications of applications, we can better fit our raw materials in order to provide the performance that's required for applications. I think that's one of the next frontiers that we'll face as a battery community. Once we've cracked these new technologies, it's about understanding how to use them, building a battery toolkit of lithium-ion batteries, sodium-ion batteries, silicon anodes, niobium-based anodes. Which technology is best fit for purpose, and how do we utilize those resources well? So to round up the presentation and to bring us into the Q&A session, there's lots of ways we can provide for this 3 terawatt-hour gap. This could be bridged by additional mine supply. It could be bridged by recycling innovation, paying close attention to understanding leakage of material that could be recycled, is counteracting any mine supplier activity. And smart next-generation battery commercialization could be used to bridge the gap intelligently. And the final thing I'll leave you with before we start the Q&A is, with that information, how is it that you would bridge that 3 terawatt-hour supply-demand gap? Okay, so thank you all very much for listening. If there's any questions at all, I'll have a look in the Q&A box now, see what's available. Beatrice, hopefully you've got a few queued up. Otherwise, please feel free to submit them, or if we miss your question, jump out over mic and we'll try our best to answer.